You have two capacitors connected in series with 40 volts across them. What is the total capacitor, the charge on each, the total energy, and then the graph. Okay, so you have here capacitor, 2 microfarads, 8 microfarads, and there is a voltage of 40 volts across. Capacitance is what here? What number did you get?
1.8.
Good, you used the right formula. It's 1/2 plus 1/8 micros. So 1/2 plus 1/8 flipped around 8/5 microfarads. The charge Q equals CV, and we know what the V is and we know what the C is, so we get a tiny, absolutely tiny, better double check that, 8/5 times 10 to the minus 6 times 40, Q equals CV, isn't it?
Yeah.
You got a really small number? 6.4 times 10 to the minus 5 coulombs. What's wrong? Oh, sorry. We didn't say anything. There, write that down if you don't have it.
But they ask for each.
Yes, in fact, when capacitors are put into series, the charge on each capacitor individually is the same as the total charge. So if you want, here Joshua, I know that each capacitor has this charge, and combined they also have the same charge. It's a little bit weird, I know, but each of those have that charge, and in total together they have that charge as well. It's because they're in series, it's a bit weird. Anyways, the next part is the total energy. So what's the formula for the energy here? Yeah, 1/2 CV squared. So 8/5 divided by 2 times 10 to the power of minus 6 times 40 squared. 5.12 millijoules? Oh, let me check that again. 1/2 times C times V squared. What did you get? 1.28 millijoules, yeah.
But the combination like
What's that, Joshua? No, go ahead, what is it?
the combination like that is equal to 6.45.
You're right. Like I said, when they're in series, it doesn't, you got to remember that the weird thing is, let me put it to you like this, when two resistors are in parallel, what is their total resistance? Like for example, if the first resistor is 1 and the second resistor is 2, the total resistance is not 3 when they're in parallel. Resistors. Yeah? So resistors, when they're in parallel, they have their special formula 1/R. Now capacitors, the situation is reversed. When capacitors are in parallel, the capacitance adds together, right? The charge also adds together. When capacitors are in series, that's when they're weird. So in series, the total charge is not the sum of the two. The total capacitance is not just the sum of the two. And likewise, the total work is not the sum of the two individually. Now the reason for this is because what will happen is when the first capacitor discharges, it then charges up the second capacitor when they're in series. So this is why it doesn't behave nicely. But when the capacitors in parallel, when they discharge, they just discharge straight. They're not trying to charge up each other. You know? So this is why it's weird here.
So if we're ever asked this question, we can't take them individually, we should just do that.
When they're in series, yeah. Now when they're in parallel, it would be okay to do them separately. But not when they're in series. So in other words, whether in series, take care. Right, the last part is the graph. Daniel, what is the graph of a capacitor for its current with the time here? So Daniel, you tell me this. Here's time, here's current, and what way will the graph look when it's discharging?
I think it goes down from the current, like this.
So it goes down from here?
Yeah, I'm not really sure.
What type of shape?
It's like just straight line.
Straight line like this?
Yeah.
No. Exponential. Like this. Okay. Anyway, Daniel, that's an improvement on your end of semester 1 exam where I gave you this question and you told me the graph was like this. I wanted to slap you. What the heck is this? So it makes me feel like people don't listen to me. Now, I'm happy that at least you said it was like this, but it's curved, is exponential. Okay? Right, that's number 5. Try number 6, please.